This mini lecture will be on the assumption of multicollinearity. One of the first things that students in my class are going to notice is that the topic of multicollinearity actually doesn't show up in Chapter 3 on assumptions in your Mertler and Vanetta textbook. It does show up in the regression chapter and some of the more advanced statistics in that textbook, but we will cover it briefly here, and then when we cover regression, it will come up again. It's a fairly simple assumption. It's not hard to understand. It's the idea when doing regression or analyses where you have multiple predictor variables that are continuous, the predictor variables can't be too highly correlated with each other, right? And so you cannot have predictor variables that are continuous in a regression that are super highly correlated with each other or particularly high. Some say moderate, but most everyone I've read says high. And that violates one of the assumptions of statistics. So why is this a problem? Well, if you remember back at the beginning of your chapter and of this whole module on assumptions, independence was one of the assumptions in all statistics. That is, when we are collecting data, when we're assigning people to groups, when we're gathering predictor variables and that sort of thing, that all of that gathering and that operation is independent. It's not that things are contaminating each other, right? So all variables should exist independently from each other in the real world. So then we can then examine them and see if they actually relate. If they relate to each other already and they're cross-contaminated, then you can't examine them because they're cross-contaminated, right? So if you think about it that way, that I think is helpful. They have to be collected and exist in truth or nature on their own. So the terminology that it's used in statistics, the fancy language for it is orthogonal, that all data needs to be independent, that needs to be orthogonal. So if two or more predictor variables in a regression are too highly correlated, then they may actually contain the same information, and on a mathematical level anyway, they are contaminating each other, right? They're too highly correlated. So this violates the assumption of independence, which specifically here they call multicollinearity. So how would you find out if you have the problem? How would you detect multicollinearity? So, if you have multiple continuous variables in your independent predictor variable for regression, right, you're going to look for it. Now I'm going to add a caveat. If you're doing a MANOVA with multiple continuous variables as dependent variables, you also don't want those to be too highly correlated. So on the regression tradition, it's multiple independent continuous variables together, right? So not with the dependent, but just the independents with each other. And then in MANOVA, it's the multiple dependent variables, which are all continuous with each other. Those cannot be cross-contaminating each other, right? So what you're going to do is you can just run a correlation. That's the easiest thing to do. And just look at all the continuous variables in your regression or your MANOVA, or if you have some more advanced models, logistic regression and path analysis and structural equation analysis, then you can check if your correlation is just too high. What's too high? Well, I've investigated this across lots of statistics textbooks, and I have found a general agreement of a 0.80 or higher correlation, which is a very high correlation. It would not happen kind of naturally in most statistics and psychology to get a correlation of 0.8 or higher. So for the sake of my class, where we need clear guidance so that we all find the same results and I can grade you, then we're going to use 0.80 as our too high correlation for multicollinearity. In regression, you can also get something called a tolerance statistic that the SPSS will give you, and a value of less than 0.1 is a problem. And your textbook does cover that whenever, in the regression chapter, it has some specific information on that. But just to make you aware, there is another statistic. Most people say that's actually the better statistic because it takes multiple things into account besides just the correlation. So what do you do? What happens if your tolerance statistic is less than 0.1, or if your correlation is higher than 0.80? What are you going to do? Well, there's not a lot you can do. One thing you can do is you can just delete one of the variables. So for instance, say you're doing a study and for some reason you studied both the whisk and the Stanford Binet or something like that, right? Like two measures of kind of the same construct. And you found very high correlations between them of 0.84 or something like that. Well, that would indicate you're actually measuring the same thing. And it's not necessary to have both of them. So you may decide, you know what, I'm just going to drop one of the two. There's lots of reasons why you might pick one or the other. There may be theoretical reasons. One of the measures may have better reliability, or one of the measures may, have better kind of like reputation as a good measure of your construct with less error in the measure. So there's lots of reasons why you might pick one over the other, and we're not going to cover that really in this class, but that is like the best kind of number one way to solve the problem. Another thing you could do is create a combination score. So for instance, maybe you're doing a study and you're doing the whisk, but you're trying to use all four subdomains for it, and it turns out that your four subdomains are really highly correlated with each other, and too highly, 0.80, or your tolerance is less than 0.1, so you're sitting there going, crud, I can't separate them. Well, you could get a combination score, and for the whisk, that's great because a combination score already exists that's validated and everyone in the field agrees to, and you can just use a total scale score on their IQ, for instance, as a combination score. So that kind of thing, if it exists, it would be great. If this problem were to occur in a homework assignment for me or a test in my class, that kind of thing, I would give you clear guidance on what to do so that we all get the same answer. And we don't have, some people deleting this, some people deleting that, some people creating a combination score, because those are all legitimate ways to solve the multicollinearity problem. Okay, so as we close out this short lecture on multicollinearity, remember, what is it? It is a way of measuring and examining that you have independence of variables, particularly, again, multiple continuous variables, all on the independent variable side, shouldn't be too highly correlated, or if you have multiple independent variables, all on the dependent variable side of things, those shouldn't be too highly correlated with each other. You can check it by checking correlations or checking tolerance statistics if you're doing a regression. And then you fix it by either eliminating one of the highly correlated variables or creating some kind of combination score. So, okay, that's all you need to know.